In this video, we are going to be looking at ionic bonding. So the first thing you need to be able to do is define what we mean by an ionic bond. So an ionic bond is the electrostatic attraction between oppositely charged ions. So oppositely charged ions mean positive and negative ions, or if you want to call them cations and anions, that's fine as well. So let's just kind of go through some examples of cations and anions. So cations are positively charged ions. So for example, our metal ions, so metals always form cations, so they always form positive ions. So, any example, so sodium ions, calcium ions, literally any metal and the ion it forms is an example of a cation. A polyatomic ion that we've come across that is a cation is our ammonium ion. So hopefully you remember ammonium is NH4+. When it comes to our anions, which are our negatively charged ions, examples of that are our group 7 halide ions. So for example, chloride, bromide, iodide. We also have our group 6 ions as well, so our oxide ions, our sulfide ions. We also have polyatomic ions that are anions, so you should have come across carbonate, sulfate, nitrate as well. So these are all examples of anions down here. Now, one kind of trick, so other than the ones that have ammonium in them, okay, you will find an ionic compound is usually between a metal and a non-metal. Okay, so for example, if you have sodium chloride, so NaCl, because you've got a metal with a non-metal, that should give you an indication that this is a ionic compound. Okay, so the only exception to that is when you have ammonium as your cation, but everything else, if you have a metal bonded to a non-metal, that should tell you you are dealing with an ionic compound. So the next thing that you guys should be able to do is draw a dot and cross diagram. Now, in my dot and cross diagrams, I'm only going to show the outer electrons, and for most exam questions, they will also say to show only the outer electrons. So I'm going to do the dot and cross diagram for sodium chloride. So that's an ionic compound, and it's formed by the ions sodium plus and Cl minus. Okay, so we're going to have these two ions involved in sodium chloride. So sodium is in group 1. If I just draw a sodium atom, the outer electron, you just have one electron. And if I draw a chloride atom, I'm going to use dots for these ones. So it's group 7, so it has 7 outer electrons. Okay, so these are atoms, not ions at the moment. When we form ions, we lose or we gain electrons. So electrons are essentially transferred. Okay, there is no kind of sharing of electrons. We transfer electrons from one place to another. And as you can see, electrons over here, so to get a full shell over here, because that's the aim of every atom, to get a full shell or an empty outer shell, our sodium here is going to lose this electron, okay? And our chlorine over here, to get a full shell, is going to want, so it wants a full shell of 8, it is going to gain electrons, or in this case, 1 electron, okay? So over here, we're going to lose this electron, and this electron is going to go over here. Now, in that process, because I've lost an electron here, I formed an ion. So we show this as an ion by putting square brackets around it, and because we've lost an electron, we're now left with a positively charged ion like that. And over here, because we've gained an electron, again we formed an ion, and because we've gained an electron, we now have a negative charge. So whenever you are drawing the dot and cross diagram for an ionic compound, you must have a transfer of electrons. Okay, so something will have gained electrons, something will have lost electrons. Because you have formed ions, you need to have square brackets around those ions and the charges for those ions in the top right corner. So that's a dot and cross diagram for sodium chloride. Let's now do the dot and cross diagram for let's go for magnesium fluoride. Okay, so magnesium starts off, so it's group 2, so magnesium starts off with 2 electrons in its outer shell. Okay, and fluorine starts off with 7 others. Because there's 2 fluorines, I'm going to draw both fluorines in. I'm going to use dots for this one. It doesn't actually matter. I could have used dots for the magnesium and crosses for the fluorine. Doesn't matter, as long as you are consistent. So we have 2 fluorines. Like that. Okay, so at the moment I just have my atoms in place. 2 outer electrons there, 7 there, and 7 there. Now again, when our our atoms want to form ions, they want to have a full outer shell of electrons. The way magnesium can do that easiest is by losing these 2 electrons. Okay, and fluorine, as you can see, each fluorine is going to want to gain an electron. So we're going to lose electrons here, have an empty shell over here. This one's going to gain 1, and this one's going to gain another. Okay, and because we've formed ions, again, square brackets, because we lost 2 electrons here, this now has a 2+ charge. Each fluorine here has gained 1 electron, so each has a -1 charge. So that is the dot and cross diagram for magnesium fluoride, MgF2. Right, let's now have a look at the overall structure of an ionic compound. Now, ionic compounds aren't just between the ionic bonds aren't just between 1 positive ion and 1 negative ion. Okay, there are going to be lots of cations and lots of anions present. And what it actually does is it forms a giant ionic lattice. And this is a very important key phrase that you need to use in any question to do with ionic compounds. Okay, so the structure that it adopts is a giant ionic lattice. That essentially means, when it says giant, it's basically a repeating pattern. So it's a giant lattice, a repeating ionic lattice. I can only do it in 2D on the board over here, but it is a 3D structure. So essentially each positive ion is surrounded by negative ions and vice versa. Okay, obviously, as I said, this would be in 3D, but between each of these we have ionic bonds. And that is essentially a repeating pattern in all directions in 3D that we have for the giant ionic lattice. Okay, so essentially so that's a positive ion. Each positive ion is surrounded by 6 negative ions. Okay, so we've got 4 in the plane of the board, but remember there's going to be 1 coming out of the board and 1 going into the board as well. So each positive ion here is going to be surrounded by 6 negative ions, and each negative ion is going to be surrounded by 6 positive ions. Okay, but the key thing here is that this is a giant ionic lattice. This is 3D, so imagine this was done in 3D. So this is a 3D structure, and it's a repeating pattern. Okay, and these over here are just the ionic bonds that I have drawn in. All right. Let's now have a look at the properties of ionic compounds. So there are 3 properties that I want to address. The first one is melting point and boiling point. Okay, you need to know that all ionic compounds have high melting point. I'm just using MP for melting point and BP for boiling point. They have very high melting point and boiling points. The reason being, so in that thing that I just drawn where we had the ionic lattice, as I said, imagine it's in 3D. So when we want to melt our ionic compound, we have to break the ionic bonds. Okay, there are no kind of other bonds here other than ionic bonds. So when we want to break our ionic lattice, we have to break the ionic bonds. And these are very, very strong bonds. Okay, because of these very, very strong ionic bonds, a lot of energy is required to break them. And that makes all ionic compounds have a high melting point and a high boiling point. Okay, so the high melting point and high boiling point is due to the strong ionic bonds in the giant ionic lattice. Also, it's worth pointing out that, for example, if we have sodium chloride, so that's made up of Na plus and Cl minus. Okay, if we compare the melting point of, let's do calcium oxide, so calcium has a charge of 2 plus and oxygen has a charge of 2 minus. Because this ionic compound here is made up of ions with higher charges, the melting point and the boiling point for calcium oxide is actually going to be higher than sodium chloride. Okay, that's due to the higher charges on the ion. So this one only has +1 and -1, whereas this has +2 and -2. Because of the higher charges, the ionic bonds are stronger, and therefore the melting point and the boiling point of calcium oxide here is greater than sodium chloride. Right, the other one that I want to address is the solubility. So ionic compounds are soluble in polar solvents. So they are soluble in polar solvents. So by that I mean water, so something that is, we will discuss polar compounds later, but water is an example of a polar solvent. The thing is, as you increase the charges, like for example, as we went from sodium chloride to calcium oxide, the greater the charge becomes on the ions, the less soluble an ionic compound becomes. Okay, so for example, in that one there, sodium chloride is going to be more soluble than the calcium oxide. Okay, but the general rule of thumb is that ionic compounds are soluble in polar solvents. Okay, and the last one is electrical conductivity. So that's essentially, can it conduct electricity or not? It's worth noting that as a solid, this ionic compound here cannot conduct electricity. And the reason being is because these ions are held in fixed positions in this ionic lattice. Okay, they can't move, they're held in place by the ionic bonds. So as a solid, we cannot conduct an electrical current because we do not have free moving ions. Okay, but if I melt this compound or I dissolve it in water, so dissolving in water does this as well, it will break these ionic bonds. Okay, and because the ionic bonds break, the ions are now free to move. And because the ions are free to move, this substance can now conduct electricity. So you need to have free moving ions or free moving charges to conduct electricity, which you don't have in the solid form, but as a liquid or when it's dissolved in an aqueous solution, it does conduct electricity.